Now that we've talked about elements and atoms and how to learn about them on the periodic table, we want to move into now talking about compounds. And so we know that compounds are pure substances composed of more than one element. And now we know that that means that they're really molecules, right? That at the smallest unit of a compound, we have a molecule, that tightly bound group of atoms. That's how they're composed of more than one element. They're composed of more than one type of atom in the molecule. And so now chemical bonds are going to be the thing, the kind of mechanism that holds those atoms together in that molecule. So we'll talk about different types of them, but we just want to start with that, kind of these ideas of compounds. So one of the things about elements that's kind of, we say that everything's made of elements, but we really only have on the order of about 100 elements. People can make new elements. You just make atoms with more protons than anybody else has ever done before. And so we can build this up. It's really slow, but there's not really that many elements. There's about 100 of them that are really functionally useful to make compounds out of. The thing is, pretty much the sky's the limit in terms of making compounds, because not only are you saying, well, what types of compounds are you going to make, or what types of atoms are you going to combine in those molecules, but how many of them, right? Do you want 2 oxygens and 3 carbons? How many carbons, how many hydrogens, nitrogens are you putting in there? So we only have about 100 elements, but really the sky's the limit when it comes to compounds. There are thousands of compounds that have been created, and really you're only limited by your imagination, right? What sort of combinations of atoms do you want to put together that someone hasn't done before, and kind of driving to make new compounds with new properties. One of the important things about compounds is that their properties are not at all related to the properties of the atoms that went into them. So for example, hydrogen and oxygen are both gases. You put them together, you make liquid water. Water is very different. Hydrogen and oxygen are both extremely reactive. Water is not. One of water's greatest properties is that it doesn't do a lot of chemistry. That's why we use it to fight fires, because it's one of the few things that's not flammable. It's a liquid at room temperature. That's really, really useful and really important. We use it for all sorts of things. And so those compounds have very different properties from the atoms. So you can make all sorts of compounds, and they can have all sorts of wild properties that aren't at all related to what those elements were. Sodium and chlorine, both highly, highly reactive and very bad for people. Sodium, highly reactive metal, chlorine, toxic yellow gas. You put them together and you get table salt, which is now part of a balanced diet to an extent, right? Balanced. It's an important part of living things, and you need it. And so, it's all of a sudden not dangerous on face. Too much is a bad thing, but that too much is a lot more. Any chlorine and any sodium is going to be too much. But so, you can change those properties and come up with a compound that has distinct and unique properties that are entirely different from the elements you started with. So when we're talking about compounds, we define them using what's called a molecular formula. As the name implies, it's the formula of the molecule. It's just going to be a list of the elements in that compound, and we're going to use shorthand. We're going to use our chemical symbols. So this is a description of the atoms in a molecule. So it's going to be the type and number of atoms. So for example, one water molecule is 2 hydrogen atoms and 1 oxygen atom. Okay, so we can see the 2 right here follows the H for the hydrogen. So you write H to say that there's a hydrogen in there, and then you put the 2 afterwards as a subscript. Okay, so that 2 is the number of atoms. You'll remember we used this top corner was for charge. We had mass number previously and atomic number. But when we're talking about number of actual atoms, that's where that bottom right corner shows up. So we have kind of all the different corners around a chemical symbol. Those different positions mean different things. And that bottom right corner means number of atoms. So in one water molecule, there's 2 hydrogen atoms. There is 1 oxygen atom. You'll notice we don't write it. Just like with the charge, we didn't write the 1 in that case. We don't write a 1 to say that that's the number of atoms I have. So we just say H2O. We don't say H2O1. There's basically just an implied 1. We don't write anything there. While the molecular formula gives us information about the numbers and types of atoms, that's not a complete picture of molecules. The atoms aren't just randomly arranged. In fact, molecules have shapes. Molecules have arrangements of the different atoms, and we convey that with a structural formula. So here's a structural formula for aspirin. So we can see a couple things. One, there are the symbols, the chemical symbols. C is still carbon, and in this case there are multiple C's, each representing a carbon atom. The O's represent oxygen atoms, and the H's are hydrogen atoms. So for now, we just need to be able to recognize that those are different atoms and that they are linked together in particular patterns. There's lines, some single lines, some double lines. Those are representing chemical bonds. So this is explicitly referencing that these two carbon atoms are joined together. This carbon and this oxygen atom are joined together with two lines. And so we'll learn what the differences are between those. But for now, we just want to be able to recognize that, hey, this is the shape of this molecule. This is the structural formula that there is a particular shape. And that's kind of the schematic one. You can also find 3D representations of structural formulas. Here, each of the balls represents an atom, and they're color-coded. These colors are pretty common. Carbon is black because graphite's black. Oxygen is red because of fire, and hydrogen is white just because it's kind of small, get it out of the way. And then there are lines connecting them for bonds. You'll note there's no distinction between the 1 and 2 lines here, so it's slightly different information, but it's all there. For our purposes, we want to be able, for now, to recognize that this structural formula and maybe take that and turn it into a molecular formula. We are not expecting to take a molecular formula and turn it into a structural formula. We'll eventually do very small molecules. Being able to do it for aspirin requires a lot more years of chemistry. But we do just want to kind of have the idea, molecules aren't random mishmashes of atoms. They have shapes, they have structures that inform kind of their properties and what they do. And we can interpret those and represent those. So let's look at an example of taking a structural formula and turning it into a molecular formula. So here's a molecule, and we have the structure, the atoms represented by the chemical symbols, and they're all linked together. So if we want to think about what is the molecular formula, we know that a molecular formula shows the types of atoms and the number of each of them. So whenever we look at this, we want to be thinking, first off, how many types of atoms do I have? Which is the same thing as how many different symbols do I have? How many different letters are in this structural formula? The answer to that is going to be 4. I have H, C, O, and N. So I know then that the structure, or kind of the shape of my molecular formula is going to look like this. C, H, N, and O. And then I just have those A, B, C, Ds because they're going to have some sort of subscript for the number. One of the things you'll note is there's a particular order that I've chosen there. Carbon is first, oxygen's last. There is a motive, there's a reason that that order is there. For now, you do not need to worry about that order. If you're coming up with molecular formulas, what's important for now is the types of atoms that you're including in the formula and the numbers you're using after them and using the correct format. It is important that the number after carbon is the right number. You can't just, it's not just the numbers and letters in any order. That's important. The carbon does always need to be paired with its number. So carbon we'll do first. We want to count out the carbon atoms. I have 1, 2, 3 carbon atoms. So that'd be C3. For hydrogen, I can see I have 1, 2, 3, 4, 5, 6, 7. So that's going to be H7. For nitrogen, I can see the N, I just have 1 N. So because I only have the 1 N, I'm not going to have a number after that. It's just going to be N. And finally, for O, I have 1, 2 O's. So it'd be O2. So I can see overall, it'd be C3, H7, N, O2. So again, for the order, you could have called this like H7, C3, NO2. But you can't say like H3C7 because that'd be wrong. That's a different molecule with a different number of atoms. You can rearrange them, but they got to stay linked up. 2 always has to be after O, and it always needs to be a subscript. It always needs to be down on the bottom. Okay, so we've talked about molecules. So now we want to get into, we can like define what they look like. Now we want to get into a little more the nuts and bolts of compounds, and they're held together by these chemical bonds. So it ends up there are two types of chemical bonds. There are ionic bonds and they are covalent bonds. The difference in the name just has to do with the fact that one involves ions and one involves atoms. Okay, where ions are charged and atoms are neutral. So when we're looking at this, we know that chemical bonds are relationships between atoms that are holding them together in a compound. And so these are interactions between atoms, which means they are mediated by electrons. And so ionic bonds involve the transfer of electrons, and covalent bonds involve sharing electrons. So that is the difference between those. And when you have ions that are held together in a compound, there are ionic bonds, which the transfer of electrons is what drives that. And in covalent bonds, you have neutral atoms, which are held together by sharing electrons. So ionic bonds make what are called ionic compounds. Salt, table salt, is an example of an ionic compound. Covalent bonds make up covalent compounds. Water is an example of a covalent compound. So that is something that you could see and use. Covalent compounds, ionic compounds all exist. They have different properties. It's not necessarily, it does affect the properties and how those compounds behave, but there are plenty of ionic compounds, plenty of covalent compounds that each have their own kind of thing. They have their own utility. So when we start talking about these, we can start by talking about ionic compounds, which are compounds composed of ions. So one thing that's important to note is that the ions are charged, but the overall compounds are neutral. So overall, your compound is going to be neutral. Sorry, that's really janky. So what that means is that they're going to have one positive and one negative. They have a cation and an anion. There's no compounds that are just anions or cations. So we know some of this language so far, but before we really dive into ionic compounds, we're going to put that off. We're going to take an aside and go take a deeper dive into what makes ions and what kinds of ions different atoms are going to form, right? We know here that there's going to be ionic compounds that are made up of ions, but we're going to take a little aside, spend a couple of videos talking about, well, what are ions and what types of ions do different elements form? All right, another video down, getting us started compounds, the next kind of big chunk of this chapter. Looking for more questions on participation 6-4. See you in the next video.